Hi everyone, I'm Jiang from University of Texas at Austin. Today, I am presenting a joint work with Yuki, Miloš, Olabi, and August, titled Comparing and Combining Analysis-based and Learning-based Regression Test Selection. Software developers write tests to check software correctness. Regression testing is a rerunning test to ensure that previously developed and tested software still performs correctly after code change, which is widely practiced by software developers. While regression testing is important, it is also time-consuming due to the number of tests and the high frequency of code changes. To combat the rising costs of regression testing, researchers and practitioners propose regression test selection to reduce the cost of rerunning all the tests after every code changes by only running a subset of affected tests. The quality of an RTS technique is evaluated in terms of its safety, precision, and performance. An RTS technique is safe if it selects all affected tests, precise if it selects only affected tests, and performant if the time to select and rerun affected tests is less than the time for rerunning all the tests. Researchers have shown that regression test selection based on program analysis, often called analysis-based RTS, can save substantial testing time for medium-sized open-source projects. Analysis-based RTS techniques use static or dynamic program analysis to find code elements, like statements, control flow edges, methods, or classes that each test depends on. Then, on a new code version, the techniques select tests that depend on modified elements. For example, the figure illustrates a dependency graph where test T1 and T2 transitively depends on class C1 and C2. In the new program version, analysis-based RTS technique select T1 and T2 when C1 and C2 are modified. However, large companies like Facebook, Google, and Microsoft did not adopt analysis-based RTS because of the analysis cost, its imprecision, and these companies' frequent use of multiple programming languages in a repository. Recently, researchers applied machine learning models to do regression test selection based on the design features. Some of them trained a gradient-boosted decision tree model on features such as test historical failing rate, distance between code elements on the dependency graph, and textual similarity between code change and test to estimate the probability that each test will fail when run on that change. However, machine learning-based RTS models require large data to be trained on, which are hard to obtain. They also cannot guarantee the safety. To this end, we want to build lightweight ML-based RTS models that give the likelihood of the test failing based on the features from the code change, while it does not require features from program analysis. And by combining it with analysis-based RTS, we can further improve the precision of analysis-based RTS. In other words, reduce the number of non-failing tests that are selected by analysis-based RTS. In this work, we first design and implement several ML-based RTS models that can be applied to medium-sized Java projects. We obtain a training dataset for our ML-based RTS models via mutation analysis that sees mutants that represent artificial faults into a program. Then, we combine the ML-based RTS with analysis-based RTS to improve their precision. Finally, we perform an empirical evaluation using 10 open-source Java projects to compare our approaches with baselines. In the first part of my talk, I will describe the technique we present in our work. Machine learning models require a large amount of training data to achieve better performance. To train an ML-based RTS, we need a dataset consist of code changes and tests with their labels to indicate whether they fail or pass. Unfortunately, a single open-source project usually does not have enough of such data on changes and test outcomes, even when using continuous integration services such as Travis CI. There generally are not enough build logs representing changes with true test failures to help with constructing a training dataset. So, we utilize mutation testing to create the training dataset automatically. Mutation testing leverages a number of mutation operators that describe rules for changing code on the test, creating variants of the code called mutants. After creating mutants, tests are run on each mutant, and we construct a large label training dataset by providing positive and negative labels to each test mutant pair. We train two types of ML models, one that learns based on tests that fail when run on mutants, and another one that learns based on tests that get selected by an analysis-based RTS technique. For the ML-based RTS model that predicts test failure after change, we assign a positive label to a mutant test pair if the test kills the mutant. Otherwise, we assign a negative label. For the ML-based RTS model that predicts what analysis-based RTS technique will select after change, we assign a positive label to a mutant test pair if the corresponding analysis-based RTS technique will select that test. Otherwise, we assign a negative label. Finally, the mutant together with the label tests are the training dataset. However, our initial training dataset is very imbalanced because only a small percentage of tests would have a positive label. The machine learning model always struggles when trained on imbalanced data. Following prior work on machine learning-based code search, we address this issue by building a training dataset where the instances are triples of the form code change C and positive label test T+, and negative label test T-. Now, let me introduce the architectural overview of our ML-based RTS model. It consists of three stages: feature extraction, feature representation learning, and likelihood prediction. Next, I will introduce the details of feature extraction. We take two steps to pre-process every instance in our training dataset to extract features. First, for all test classes, we split the test class name into tokens via camel case and snake case and convert to lowercase. For example, the test class string tokenizer test will be tokenized into three tokens: string, tokenizer, test. Second, for code diff, we preprocess and extract features from the change. We use three approaches for feature extraction. First approach, we call it basic. We use the class name of the change class file as a feature. Our intuition is that class names often give some indication of the class functionality and the relationship between test and code under test. We tokenize change class names in the same way as the test class name. Second approach, we call it code. We consider a file-level code diff that consists of added and modified lines in the commit. We assume that the size and contents of the code diff will help the model to select positively labeled tests. Specifically, for each changed file, we extract the sequence of tokens on added and modified lines. We tokenize lines by space and punctuation, and then we tokenize further in the same manner as the test class names. Finally, we concatenate the tokenized version of the changed class name with the tokens obtained from the added and modified lines. The third approach, we call it ABS, which means abstraction of code diff. The actual code diff and change lines may not generalize to unseen or future code changes. To mitigate this issue, we define rules that map parts of the change lines of code to general operators, namely the mutation operators that we use to create the training dataset. The detailed mapping rule is presented in the paper. Given a code diff, we go through each line and check if it matches the defined patterns. After matching, we abstract the code diff as a sequence of mutation operators. We concatenate the tokenized version of the changed class name with a sequence of mapped operators. Next, we describe the feature representation learning stage. We use two encoders. The first encoder, test encoder, encodes features from the tests. The other encoder, diff encoder, encodes features from the code diff. Both encoders are instances of a bidirectional gated recurrent unit network, which is a variant of a recurrent neural network. To be specific, considering a sequence of tokens are embedded into vectors through an embedding layer. The test encoder encodes that sequence of vectors and outputs the sequence of encoded vector representations HT. Similarly, the diff encoder outputs the sequence of encoded vector representations HC. Both sequences of vectors capture the semantic information of test and code diff. We apply an attention mechanism which is widely used in machine learning areas such as computer vision and natural language processing to learn a representation that captures the mutual relation between two vector representations. In our ML-based RTS model, we use attention mechanism to get a vector representation from test feature vector and a code diff feature vector. Then, we feed the learned representation into a multi-layer perceptual network, which is a neural network with two linear layers and a ReLU activation function with sigmoid function to output a score between 0 and 1. We train the ML-based RTS model to predict the scores for positive examples T+, and negative examples T-, and get the likelihood score S+ and S- respectively. And then we minimize the ranking loss with the formulation shown in the slide. In the loss equation, M is the user-defined margin. The ranking loss encourages the score between code changes and positive label tests to go up, and the score between code change and negative label tests to go down. Remind that we train two types of models, one that learns based on tests that fail when run on mutants, another that learns based on tests that get selected by analysis-based RTS technique. From a combination of what the ML-based RTS model is trained to learn and the type of features that are extracted from code changes, we train a total of 6 models shown in this table. Models with names starting with fail are trained to select failing tests. Models with the name starting with ecstasy are trained to select affected tests as ecstasy. At the last step, we combine analysis-based RTS and ML-based RTS by using our proposed ML-based RTS models on top of an existing analysis-based RTS technique. After the developer makes a change, an analysis-based RTS technique can first analyze those changes to do an initial selection of tests. Then, ML-based RTS can use a previously trained model to rank the tests selected by analysis-based RTS by assigning a score to each test based on its relevance to the change. In the second part of my talk, I will describe the empirical study and the results we have. We consider two baselines in our empirical study. One is the information retrieval-based RTS model. It uses IR metric BM25 score to rank tests based on their relevance to code changes by treating each test file as a document and the code changes as a query. The ranking is based on assigned scores to each test. The other baseline is an ML-based RTS model called EAL RTS. It is trained using random forest model to select tests based on features from a dependency graph extracted from its starts and the project's Git commit history. We perform our evaluation on 10 open-source Java projects that were previously used in prior work on regression testing. These projects use Maven and JUnit 4 as required by Ecstasy and Starts. For each project, we select an early commit to create training data, where we could build the project with no test failures and run analysis-based RTS tools. Unlike prior work, we do not train the model using some mutants and then evaluate on the remaining mutants. Instead, we build an evaluation dataset for each project by leveraging its real code evolution. We first select commits that are after the training commit as the evaluation commits. Then, we introduce failing tests by mutating the code changes in those commits. Specifically, we compute the Java source file lines that differ between the commit and the previous commit. Say we have n changed files between two commits. We then apply a different mutation testing tool, Universal Mutator, to create mutants that modify only the changed lines in the changed files. To avoid the problem that most mutants modify the same file, we limit the number of mutants per file to 3, namely, randomly selecting 3 generated mutants per file. After running Universal Mutator, we'll have a bunch of pairs of mutants and the commits where they are generated from. For example, each mutated file shown in this figure and the commit SHA2 will form a pair of mutant and commit. We then run all tests on each pair of mutant and commit to collect tests that can fail. We use the resulting set of code changes and test failures as our evaluation dataset. In evaluation, we run our ML-based RTS models to select the failing tests from the tests selected by an Analysisbased RTS tool. To evaluate the models, we measure for each pair of mutant and commit the percentage of tests out of all tests in the test suite that the model will need to select to run all failing tests. Lower selection rates are better. We also measure the overhead of using each analysis-based RTS technique and combining it with ML-based RTS models. To compare between different tools, we report the best safe selection rate, which is the largest selection rate needed to select all failing tests across all pairs of mutants and commits in each project. We also report end-to-end testing time, which is the summation of the time to select tests and the time for running the selected tests such that all the failing tests are included in the selected test set. Next, I will present the results and findings. In the bar plot, we show the number of times among 10 projects that fail-basic EAR RTS and BM25 model has the lowest best safe selection rate, namely performs the best among all the baselines, while combining with ecstasy or starts. We find that no single model consistently outperformed the rest among all 10 projects. The best model, fail-basic, outperforms other baselines on 7 projects when combining with ecstasy. In most projects, fail-basic model outperformed the BM25 model and the EAR RTS model. In the bottom left bar plot, we show the best safe selection rate of fail-basic BM25 on 3 projects when combining with ecstasy. To better compare, we also show ecstasy best safe selection rate not combined with any models. In the bottom right bar plot, we show the best safe selection rate of fail-basic BM25 on 3 projects when combining with starts. Similarly, we also show starts best safe selection rate not combined with any models. We can see that combining fail-basic with analysis-based RTS better improves the precision of ecstasy and starts compared with BM25 model. In the bottom 2 bar plots, we show the end-to-end testing time when combining fail-basic models with ecstasy and starts compared against that time for ecstasy and starts alone on 3 open source projects. Overall, end-to-end testing time for fail-basic combined with the analysis-based RTS technique is less than the corresponding analysis-based RTS technique. In conclusion, we find that, first, when combining ML-based RTS models with analysis-based RTS techniques, our best ML-based RTS model reduces the average selection rate of 2 analysis-based RTS techniques by 25% and 21% respectively, while still selecting all failing tests. Second, combining ML-based RTS models with analysis-based RTS technique results in reduced end-to-end testing time, suggesting that the overhead of the ML-based RTS models are small compared with analysis-based RTS techniques, and substantial time savings result from running fewer tests than what the analysis-based RTS technique selects. We have open sourced our data and code. Please do check our paper for details if you are interested. Thank you.